All right, so we're shifting gears now. We're going to be talking about something pretty new, and which I think in your pre-calculus class you might have talked about sequences at least, and maybe not infinite series, but some types of series, finite series. In fact, in calculus 1, I think you probably saw a little bit of the notation. Anyway, let's go ahead and talk about sequences today. So this is 11.1. So we have to talk about sequences first because they are sort of foundational to what we're really studying, called series. So really what a sequence is just a list of items. That's it, really, a list of elements, numbers usually. So let's take a look at the first example and you can kind of just see what they are. Fundamentally, they're pretty easy to comprehend. It's just, like I said, a list of items, a list of numbers usually. And that list can be given a formula that will tell you how to find each element of the sequence. So in this case, we're told that the formula is n minus 1 over n plus 1. What we have to also kind of realize about sequences is it's not just a list. There's a bit of definition behind it, and you can see the definition right there at the top of the worksheet. It says sequence is defined as a function. So it's a function is really what we're talking about here. And the important thing is that the domain is the set of the positive integers. Okay, so that's important. The domain is the set of positive integers means that this is the domain. It's just a set of numbers that are the input values, and then the sequence itself will determine what the output values are. So this is important again because this is always the domain of any sequence. Whenever you're talking about a sequence, the domain is understood to be the set of natural numbers. Okay. And so, like for example, in this one, we can start listing out the terms of the sequence based on the formula for the sequence. If the first, again, the domain of any sequence is always all natural numbers, so you always have to start with 1. And so when you start with 1, you see that the output is 0. When you put in the number 2, you see the output is 1/2, right? Oh, no, I'm sorry, 1/3. And then if it's 3, then we get 2 over 4. I'll just leave it unsimplified. And then 3 over 5, and so on. So if you were to start listing out the terms of this particular sequence, that's what they would be. Those would be the output values. Okay. We also have these other types of sequences that are defined recursively. And if you've taken any computer science, you might be familiar with this idea of recursion. In math, we have a recursively defined sequence. In this case, the elements of the sequence are the C sub n, and the notation that we use here, the subscript is basically just referring to the nth term of the sequence, and so n is based on what these numbers are right here. So we would start with n equal 1, and then we go to n equals 2 and 3 and 4, etc. And so we can refer to very specific terms in the sequence, like what's the 5th term, what's the 7th term. In this case, we determine the terms of the series recursively, where we're told what the first one is, and this has to happen in a recursive sequence, because of the way that a recursive sequence is defined. The way it's defined is that we find any element of the sequence based on elements that came before it, or elements that came before it. And so you have to have a starting point, and that's why any recursively defined sequence have to have that first term given, and then you have a formula that will tell you how to find all the terms after that. So we can start listing the terms of this particular sequence here, the C sub n ones. The first one is 2, obviously, and then the next one, how do we get the next one? Well, we take the first one, this would be like n equals 1, to find the second term. So we have to plug in the first term to find the second term. Okay, so what was the first term? It was 2, so I would take that first term, multiply it by 2, add 1, get 5. And so that's the next term. And then you can do that to find the third term too, except now we're using the second term to find the third term. So I multiply that second term by 2 and add 1, I get 11. You can kind of see where this is going to go. So what's the next term then? You guys see how this is going? Yeah, 23. And then after that, everybody see how this is working? Yeah, 47, exactly. And then it just keeps going in this pattern here. So you can identify any term of the sequence, but you need to know the term that came before it to figure out what the next one's going to be. Sometimes you'll see that the formula for a recursively defined sequence requires you to know the previous 2 terms, maybe even the previous 3 terms or whatever. But however many terms you need to define the nth term, you would then have to be given that many terms at the start. You see what I mean? So suppose I had a recursively defined sequence. that needed to know the 3 terms before it to figure out what the 4th term is going to be. Well, then you would have to be given the first 3 terms in order to get all the terms after that. All right, so important thing that we need to know about for series, which is really what we're going to be mainly interested in, is the idea of the limit of a sequence. And so you can read about that there. The limit is you can find the limit of a sequence really by finding a function that would correspond to that sequence for every x value. Okay, so in other words, what we do, in fact, let's just do this example to demonstrate how this works. So suppose I want to find the limit of this particular sequence, 3n over root n squared minus 2. How do I find the limit of the sequence? Well, you can read right above that how we actually do that. We need to find a function that matches the terms of this particular sequence for every value of x. And so the function that we find, and it's real simple, is we basically just look at the sequence and we turn those n's into x's. But just realize that these are not fundamentally the same thing, right? The sequence has, by definition, only the integers, positive integers, as input values. A function, on the other hand, unless you state otherwise, it has its natural domain. That is all the x values that you can plug into it and expect to get some number out, right? Well, if you look at this function here, the natural domain of this function definitely includes numbers that are not integers, and so that's the difference there. But really, fundamentally speaking, all you have to do to find the limit of a sequence is simply change those n's into x's and then use what you know about functions and how to find their limits to find the limit of the function, and therefore also the limit of the sequence. In practice, though, you don't really even have to change those n's to x's, because everything that you do to the x's, of course you could do the same thing to the n's, so really this is just sort of mathematical way that we define what the limit of a sequence actually is. In practice, you don't even really have to change the n's to x's. Anyway, now we do have to remember how to find these limits. So thinking back to our calculus 1, what we have to do for this particular one is multiply by the highest power of x that occurs in the denominator. And then what we have to remember here for that type of thing is that for large values of x, that denominator term, x squared minus 2, acts like just x squared. You guys remember that from your calculus 1? Basically what that's saying is if you have large values of x, and we're talking very large because what are we doing? We're going to infinity, right? So hugely large, right? Billions, trillions, quadrillions, right? If you take a really big number and you square it and then you subtract 2 from it, well, that subtraction of 2 is really not going to do anything, right, in the long term. And so we can basically say that this function acts like x squared, the square root of x squared, which is just x. And so that means that what we need to do to find this limit is multiply the numerator and the denominator by 1 over x. Or if you want to just say divide the numerator and denominator by x, that's fine. And then that gives us this. And then remember, the next step on something like this would be to try to incorporate that x here in the denominator with the root above it. And so we just say, well, x is equal to the square root of x squared. Nobody would argue with that. And then when you have a root over a root, you can put them under the same root. So you get x squared minus 2 over x squared. Then you can split that thing up. If you split it up, you get x squared over x squared, which is just 1, and then minus 2 over x squared. And then you can say, okay, well, what happens now when you take the limit as x goes to infinity? Well, we know that that term there is going to go to 0. And so what are we left with? Over 1, or just 3 over the square root of 1, or just 3. So the limit of this particular function is 3. And so therefore, by that limit of a sequence theorem that we're looking on the page there, say, so the limit of the sequence is the same thing as the limit of the function. Okay, does everybody see what we're talking about here? So this limit is 3. Doing this limit to the function, and then the theorem there tells us that the limit of the function and the limit of the sequence are the same thing. But again, like I say, in practice, you don't really even have to change those things to x's. I would be fine if you just left them as n's and did the limit that way. It's the same thing. So, okay, squeeze theorem for sequences. Basically, the squeeze theorem for sequences says pretty much the same thing the squeeze theorem for functions. For this particular sequence here, cosine pi n over n squared, the procedure here is to start out by saying, okay, let's look at that numerator term there and think about what's true about that. Well, just based on the range of a cosine function, we know that the cosine, no matter what the input is, the output always has to be between -1 and 1, right? And then that's a true compound inequality, and that's basically just a statement of the range of the cosine function. And since this is a true statement, I can then divide all terms of that inequality by the same thing, and so I'll just divide everything by n squared, and then I'll look at the two limits on the n's here, like what's the limit of this one here? Limit as n goes to infinity of 1 over n squared, -1 over n squared. We know that has to be 0, and then if I look at this one here, I know that the limit as n goes to infinity of this thing, +1 over n squared, that's also 0. And so since both of these have the same limit, and this inequality is true, basically what that means is that the other function in the middle here is forced to have the same limit as the ones on the smaller one and the bigger one there. So what we can say by the squeeze theorem is that the limit of this function here, this sequence here, has to be 0 also by the squeeze theorem. Okay, so that's it. In fact, if you wanted to, let's go ahead and your calculator, you probably are learning a lot more your calculator this semester than you had in several other semesters, because we're using a lot of the functions of the calculator that we haven't before. So let's go ahead and, if you have your calculator, let me just share mine and so you can see. Okay, so what I just want to show you here is that your calculator can actually also graph sequences. And how do we do that? Well, we go to mode again. Go to mode. If you have your calculator, go ahead and follow along. Notice we've already learned about two modes before that we maybe hadn't seen before, right? Parametric and polar. Well, look at that last one, sequence, right? That's the last mode that we're going to look at here. Now, when you enter if you are on sequence and you enter your y equals, you're going to be entering the sequence itself. Let's take a look at that sequence we just saw, cosine pi n. Notice it also has an n min value there. That means if you want to start it at something besides 1, you can on the calculator at least. But just remember that fundamentally speaking, domains of any sequence have to be just all positive integers. However, on the calculator, you can make it start somewhere else. All right, so we're going to graph the sequence here, cosine pi n. So cosine pi, and then if you want to n, that same button that we've been using for all the other variables is there. Cosine pi n. Let's change the window. We'll go 0. Let's go out to about 10, I guess, and see what happens. And then for these, we're not going to go above 1 or below -1. So I'm just going to, I'll put -1.5, I think. Okay, so you can see the little dots on there. These graphs are a little bit harder to look at just because of the low resolution on the calculators, and some of them are actually colored, which is nice. But you can see how this function is working, right? You have these dots that sort of alternate from positive to negative. If we were to continue this, like maybe graph it on paper, in fact, let me go ahead and stop sharing that. So let me just show you, if I were to draw the thing, what it would look like. So basically, that function, you have 1, 2, 3, 4, whatever. It sort of bounced back and forth, like made it alternate like that. If we were to graph that 1 over n squared function, what we would find is it does something like this. Right? You see it's kind of getting closer and closer to the x-axis there. The other one, the lower one, would do something like this. And basically what the squeeze theorem is saying is that all those black dots that I have drawn there, all these black dots, where are they always going to be? They're all going to fall between the red dots and the blue dots, you see? And so as we go further that way, that continues to be true, right? The blue dots and the red dots are heading towards 0. The black dots, for the function we're actually interested in, those ones are squeezed between always. And so as we head towards infinity, the red dots and the blue dots get closer to 0. That means that the black dots have to also. Okay, so that's the squeeze theorem. All right, and let's move on. So just so you know what that is, yours is only showing 1 dot. Yeah, so probably it might be the window. I'm not really sure. You can actually change what the dots look like if you go into the, I'm not even sure how that works. Let me see. It's probably in settings or something like that. Oh yeah, if you go into the mode, you can also see that there's a way to connect those dots. That's not very accurate if you're graphing a sequence because they're not supposed to be connected, right? But if you want to kind of get a sense of where the next dots are, you can change it over to connected, and that'll at least show you from one dot to the other how you're going to get from one dot to the other. So anyway, I hardly ever use that function on the calculator, the sequence graphing. It's not really that beneficial, but anyway, you know it's there. So all right, then we have these limit laws for sequences. Note that those limit laws are exactly the same as the limit laws that we saw for functions. It's just the only difference now is that we've replaced the x's with n's. That's pretty much it. But all those limit laws that we saw for functions, they all apply exactly the same way for sequences. So I'm not going to go through them. You can read about them there, and we'll use them as necessary. All right, some things that are actually different, though, as far as function limits versus sequence limits. There are certainly some differences, and we'll talk about one of them right now, the absolute value theorem. Absolute value theorem, AVT. So this is a useful one. We'll be using it sometimes. And notice what it says here. A lot of this section that we're dealing with now, this chapter that we're dealing with, a lot of theorems in here. And we're not going to prove them, but we do have to be aware of how they work. And so here's our first one. So if the limit of an is equal to 0, then the absolute value, then the limit without the absolute value is also equal to 0. Useful because basically what that says is that if you can demonstrate that, if you can take the absolute value of a particular sequence and show that its limit is 0, then you can drop the absolute value off of it and conclude that that one is also going to be 0 as a limit. Okay? And I'll show you kind of how we'll apply that in a minute here. Okay, here's another theorem. If you have any sequence that looks like this, with r greater than -1 but less than or equal to +1, then it converges. Okay. What does that word converge mean? Well, we've already seen that, remember, in the context of improper integrals, right? We talked about improper integrals converging or diverging, right? What does it mean for an improper integral to converge? Remember what an improper integral was? It was that thing an integral that had an undefined value at one of its bounds or somewhere in between on its domain, right? And we said that if you do the whole setup for that, make it into a limit, find that limit, and find that limit actually produces a number, well, what does that mean? That means it converges, right? And if it is infinity, or for whatever reason it doesn't produce a limit, then it diverges, right? So when I use the word converge in this context, it means the limit is existing versus it not existing. Okay, so just for example, like just a quick one here. Suppose I say here's a sequence. One thing about the notation here, the notation for sequences is takes a little bit of getting used to. When you put those squiggly brackets around it, that basically means that is the sequence itself. So sequences are normally denoted by having that squiggly bracket on the left, list out some terms of the sequence, and then put a squiggly bracket on the right. Suppose that I have a sequence that looks like this. 1 over, let's say 1, I don't know, it doesn't even matter, 1/5 to the power of n. And then again, what this notation is denoting that this represents an entire sequence, all of the terms of the sequence listed out, and there would be infinitely many of them, right? And so you can kind of start to think about what the terms of that series would actually be, right? 1/5 would be the first term, and then 1 over 25 would be the next term, right? And then 1 over 125, right? Basically what that's saying is that if you think about what happens in the long term here, what do these terms tend to be approaching? What number do they tend to be approaching? Well, it's pretty obvious that these ones are approaching 0, right? The further we go out in that sequence, the closer those values are getting to 0. And so therefore the limit is 0. But this theorem is telling us that. Everybody understands what I'm saying here. The r value here is 1/5, right? And 1/5 is less than 1, so therefore this thing converges to 0. Okay. So in other words, the limit as n goes to infinity of 1/5 to the n. And remember that these sequences exactly the same way as functions do as far as limits are concerned. If you look at it that way, that's clearly going to go to 0, right? But again, the theorem tells us it's going to go to 0. All right, so that is definitely a very important theorem. We're going to make heavy use of that one. Let's do the fourth example here. It's asking us to determine whether this thing converges or not. Okay, So now, again, notice the slight difference in notation that I'm using here. And I'm going to try to explain the difference. See, in this here, when you put the brackets around it like that, that's telling you that that itself is the sequence, okay? Like you could list it all out and get that. When you do something like this, when you just say AN is equal to that, now what that is, that does not represent the entire sequence. What this is representing is just the nth term of the sequence. So you could certainly produce the sequence from that nth term, right? Like you could say, okay, well, what's the first term? Well, the first term is the number that I would get if I plug in 1 for n, right? And so in that case, it would be what? 1 would be the output, right? So the first term of this particular sequence would be 1. So I can use the nth term to list out the terms of the sequence if I need to, right? So it's very subtle difference here. The difference here again is that this represents the sequence itself when you put the brackets around it. That is the sequence. You can write out the sequence in longhand if you want to. When you write it like this without the brackets, it doesn't represent the entire sequence. It only represents the nth term. But you can use the nth term to find the sequence if you want to. Okay. Anyway, to answer the question on this one, what we need to do is take the limit as n goes to infinity of this whole thing. Now, those limit laws that we talked about for functions, like I said, they all work for sequences as well. And so what we can do is split this up as two different limits, okay? And then notice that on that first one, that's 0. The second one, what we'll do for that second one is notice that if I take the absolute value of that thing, and I'm looking at that absolute value theorem, the one that I said we'd be using somewhat.
Wouldn't the limit on that first one be 2?
Oh yeah, sorry, 2, not 0. I don't know why I put 0 there. Be 2, not 0. Thanks. Then, so on this one, notice that when I take that absolute value, what happens? What is the absolute value? What is the -1 to the n actually doing as far as the sequence is concerned? It's just making every other term negative. You see what I mean, right? Like the first term would produce a negative value. The second term would then be positive because if I raise -1 to the second power, it becomes positive, right? And so what this -1 to the n term is actually doing as far as the sequence is concerned, it's making every other term in the sequence negative, okay? And so when I put the absolute value bars around that term, well, that's going to take away all of those negative terms, making the sequence this. So the absolute value just changes it to that. It basically just takes away that -1 to the n term. Okay, and then I can say, well, what's the limit of that? Okay, well, that limit is 0, exactly. And so if you go back up to that theorem, right, scrolling back up to the theorem, absolute value theorem, right, what does it say? It says if you take the absolute value and show that it's 0, well, what does that mean? Then the limit of the sequence itself is 0, right? So by the absolute value theorem, we know that the limit as n goes to infinity of this term, just without taking the absolute value, is also 0. That's by the absolute value theorem. So that's the use of that theorem. Basically, again, it tells you if you take the absolute value and show that that's 0, then you can drop the absolute value and that sequence will have the same limit of 0 as well. All right, so let's try the next one then. So part B. Oh yeah, I guess to answer the question on that last one, then the limit would be 2, right? 2 plus 0 is 2. So the limit would be 2 overall. So here, same idea. We can split this up as two limits. So we can say the limit as n goes to infinity of this a sub n, we can split that into two different limits. Okay, now for that second one, all we need to do, again, is just look up at that theorem, the theorem that's right above problem or example 4. If this base, you know, we have a sequence where this is the base, that's r, is being raised to some power, nth power, right? All we really need to do is look at what that r actually is. And say, well, is that r between -1 and 1? And it clearly isn't, right? This is bigger than 1. And so what is the conclusion then? Diverges, yep. Because of the fact that that r is bigger than 1. And so as we go to infinity on that, as the n values go to infinity, then the terms of the sequence itself are going to go to infinity as well. All right, this notion of being a monotonic sequence, that basically just means that the sequence is either always increasing or it's always decreasing. Okay, so when you see that word monotonic, it basically just means the function is either increasing. In fact, the technical term is non-decreasing or non-increasing. Why do we have to say that? Because that means they would also include constant sequences to be monotonic as well. Notice that the equal to signs are on all of those. That means you could have a constant sequence, all the terms just being exactly the same. That would also be considered monotonic. But really, when we talk about monotonic sequences, we really refer to the terms of the sequence either always increasing or always decreasing. Oh, and bounded sequences, those are pretty much just what they say. Bounded just means that all the terms of the sequence, if you say bounded below, all the terms of the sequence are above that lower bound. Bounded above, all of the terms of the sequence are below that upper bound. Okay, so when you talk about an upper bound for a particular sequence, it's just a number for which all the terms of the sequence are smaller than that number. A lower bound is a number where all the terms of the sequence are bigger than that lower bound. All right, so bounded and monotonic, we have an idea of bounded and monotonic just means if it's both, then it's considered, if it's both bounded and monotonic, then we know it will converge. Okay. Okay, so let's try, I'm going to actually skip to example 6 because that's talking about bounded and monotonic, and then we'll come back to example 5. That was just seeing if we can determine a formula that will tell us the nth term. All right, so let's determine if if the sequence with these terms is bounded and or monotonic. Okay, so there's really two ways to determine whether a sequence is monotonic, and remember that means it's always increasing or it's always decreasing. The first way to do, and they're pretty different methods, so I'm just going to go through both of them. Method 1 is just directly check, is it monotonic or not? So that means I just want to check, how does the a sub n term compare to the a sub n plus 1 term? And then I'm going to put a box here to say, which way, if any way, does this go? Does this point this way, possibly, or does it point that way? And if it points in either of those directions, then we can say that it's monotonic. If I can't put any inequality there, then it's not monotonic at all. Okay. So the way that we approach this is we say, okay, well, what is the nth term? The nth term is just what's written, right? 4n over n plus 3. What is the n plus 1th term? Well, the n plus 1th term would be the term that I get when I replace n with n plus 1. And so I just replace the n with n plus 1. And then I'm going to, again, I'll put this box here to say, eventually I'll be able to say, is it going to go that way, or is it going to go that way, or neither? Okay, so that's the idea. That box will represent for us for now some direction of inequality, either greater than or less than. So let's simplify that. We get 4n over n plus 3. I'll put the box. All right, so then simplifying the right side, 4n plus 4 over n plus 4. Okay, now keeping in mind that this box represents either an inequality pointing to the left or pointing to the right. So whether either way, whether it's pointing left or to the right, it doesn't really matter. I can still treat it as an inequality or an equal sign, and then provided that I don't multiply by a negative number, that sign of that inequality will remain pointing in the direction that it's pointing. In other words, what I can do here is treat that thing as an equal sign and cross multiply this thing, which is what I'm going to do. Cross multiply. And then just distribute, so you get 4n squared plus 16n. Put the box, 4n squared. Let's see, that's going to be 12 plus 4, 16n, right? 16n, and then plus 12. Okay, at this point, we can say, look at this inequality. We can subtract 4n squared from both sides. We can subtract 16n from both sides, right? And that, if we do that, that's going to leave me with a 0 here and a 12 here. So now we are at a point where it's obvious that this thing has to point this way, right? There's no question about it anymore, right? 12 is clearly greater than 0, no matter what n is. And so that means that we can follow that box that we were using all the way back to the beginning. And so now we can verify that indeed the n plus 1th term is bigger than the nth term. Okay? Well, if the n plus 1th term, that means that as you go down the terms of the sequence, I mean, what's going to happen? Every term that comes after the one you're looking at is going to be bigger than the one that came before it, right? And so what would we call this then? The n plus 1th term is definitely always bigger than the nth term, right? And so what is our conclusion? Is this monotonic? Well, since we verified that indeed the n plus 1th term is bigger than the nth term, no matter what term we're on, that means it's definitely monotonic increasing. So this is definitely a monotonic sequence. And really, we do usually specify how it's monotonic, as in monotonic increasing versus monotonic decreasing. Okay, so if the n plus 1th term is bigger than the nth term, it's monotonic increasing. If the n plus 1th term is smaller than the nth term, it's monotonic decreasing. All right, so now let's check if it's bounded as well. Is this sequence bounded? A sub n equals 4n over n plus 3. Well, I think you can see that it definitely is bounded. In fact, it's both bounded above and below, because if you notice, what is the first term of this sequence? A1. What's the first term? Well, that's the term that I get when I plug the number 1 in there, right? So 4 over 4, 1. So the first term of this sequence is 1. Now, I can now use that fact to say the first term is 1, and I also know this thing is monotonic increasing. So that means that it can never decrease. Any term after this will never be less than the number 1, right? Because it's going to be monotonic increasing. So what does that mean? That means 1 has to be a lower bound, right? It will never dip below 1 because that's the first term, and every term after that has to be bigger than that. So this is a lower bound. Okay, then you can also think, okay, well, what would an upper bound be? Well, let's see, does it have a limit as we go to infinity? If it has a limit, then that limit has to be the upper bound. So if I take the limit as n goes to infinity of this thing, well, you can see that limit's pretty easy to find because these are both first powers, right? And so what do I look at? I look at the coefficients, right? 4 over 1. So the limit of this thing is 4. And this must be an upper bound. Again, because if that's the limit, that means that it's definitely approaching the number 4 as we go to infinity, but it will never actually reach the number 4, and so therefore it can't go bigger than the number 4, right? If it did, then that would mean it would have to head back down to the number 4, but it can't do that because we already determined that it's monotonic increasing, so it can never decrease. So it is definitely monotonic, and it is definitely bounded. So in fact, it's bounded above and it's bounded below. Now, just one other thing, in case anybody's like thinking about majoring in math and going on into anything further than this, really further than the calculus sequence, if you're going to take any sort of a proofs class or anything like that, intro to proofs or stuff like that, you will be talking about this idea of lower bounds and upper bounds for sequences. In fact, any number below number 1 could be considered a lower bound also, right? Like I could say negative 10 is a lower bound on this particular sequence, right? Because all the terms of this sequence are below or above the number negative 10, right? So that's still considered a lower bound. And likewise, I could say the number 50 billion is an upper bound, right? Because no terms of the sequence are above 50 billion, so that's an upper bound. However, these two bounds that we're looking at right here, they have significance because this is the greatest possible lower bound. Any number that's bigger than 1 cannot be considered a lower bound because there'll be terms of the sequence that are bigger than 1, right? And then this is the least upper bound. That's the smallest upper bound you can possibly have. And so this notion of having a what's called greatest lower bound, you would even see if you take an analysis class, you would be seeing that abbreviation quite a bit. And least upper bound. These are important notions in if you're going to go on and take like proofs class or stuff like that. Greatest lower bound, least upper bound. For the purposes of us, we don't really care though. All we need to know is that it's bounded. Oh yeah, and I guess I didn't talk about the other method to determine bounded or to determine whether it's increasing or not. The other method is actually just something you've already seen from Calculus 1. So what's method 2? Check the corresponding function, check this function for increase, decrease. So I'm going to now look at a function and I'm going to use Calculus 1 techniques to say, where is this function increasing, where is it decreasing? And if you remember from your Cal 1, the way that you do that is by you taking the derivative. So you would take the derivative of the function, low d high, so let's see, x plus 3, derivative of the top is 4, minus high d low, so just 4x there, over low squared, right? And so that gives us 4x minus 4x, it's going to just be 12 over x plus 3 squared. And if you notice this derivative, what's true about this derivative? It's always positive, right? The derivative is always positive for any value of x. Okay, see that? No matter what I plug in for x here, since this is squared, I'm always going to get the same thing, right? And if the derivative is positive always, what does that mean about the function? Always. Well, if the derivative is positive, the function is increasing, right? So by our calculus 1 stuff, since the first derivative is positive, function is always increasing. And when we see increasing, we should know monotonic increasing for sequences. And so the sequence itself for n over n plus 3 is monotonic increasing. Okay, that's the other method. If you want to use the derivative, that's perfectly fine as a way to tell if it's monotonic or not. Oh, I guess I forgot to do one example. Let's go back and do example 5. All right, so let's look at number 5. All this one is saying is that if you, as we saw at first, you might just be given the formula for a sequence and then asked to list out the terms. Well, what if you're just given the terms and you want to find a formula? So that's what we're doing here. Given the terms, can we establish a formula that will tell us what these terms actually are? And so this is kind of just pattern matching. It's like a little game, I guess, if you want to think of it that way. Can you figure out what the formula is that will produce these particular terms? Okay, so let's see. What is a sub n, in other words? Anybody see what that formula is? What should go in the numerator? So you see in the numerator, we got 2, 4, 6, 8, 10, 2n, exactly, 2n. And remember that, you know, the n, the first n you always have to be thinking of n equals 1, right? Has to be n equals 1. What about the denominator term? What's that going to be? 3 to the power of n, exactly. Everybody see how that worked? You just look for a pattern, see if you can figure out a formula for that particular pattern. Some of them are not that easy, actually. Some of them are kind of hard to figure out. And if you're ever asked to find the formula for a recursively defined sequence, yeah, good luck with that. Those are kind of really hard to figure out what the formula would be. I don't think we actually do that in this book, so don't worry about it. Oh, one other thing. On that first example, sorry, the first problem that you guys are about to do, you'll notice that in part B, you have that factorial symbol on there. I just want to make sure everybody knows what that means. That exclamation point does not mean yell n plus 1. It actually has a very specific meaning. When you put that exclamation point after a number, like say 5, again, don't yell 5, just say, what is that? It's 5 times 4 times 3 times 2 times 1. Basically, the exclamation point just means that you're going to take that number and multiply it by all the numbers that come before it, all the way down, all the integers that come before it, all the way down to the number 1. Okay? So you can see that this factorial thing is only used for sequences. This would not be something that we would see in regular functions. In fact, if you see this, it doesn't even make any sense. Right? How would that make sense? X factorial. Because x requires a domain of all real numbers usually, or any number in between any integers. And what does it mean to talk about 2.5 factorial? It doesn't mean anything. So this symbol, the factorial symbol, only applies to whole numbers and positive whole numbers, in fact. So and notice how fast that particular thing grows, right? 5 factorial already is a pretty big number, right? 120. Think about what 100 factorial would be, right? 100 multiplied by all the integers that come before it all the way down to the number 1. It's extremely fast growing, faster than exponential functions, in fact. In fact, there's only one other function that grows faster than it, one other sort of elementary function that grows faster than the factorial. That's n to the n, in case you're interested. But yeah, factorials are very fast growing and only work with sequences in series, not with regular functions. So with that in mind, go ahead and do these 4 problems. Shouldn't take you very long. I'll give you maybe 10 minutes to do these. Okay, let's go ahead and go through this the problems here. So in that first one, you can see there's the terms that are listed. That's basically just plugging in the numbers. That's all you need to do there. And then second one, you guys see what those are, right? 1/2, 1/6, 1/24, I guess, and so on. And then 1/120. And let's see, number 2, does it converge or not?
I was going to say on that one, I was looks like I was writing out the terms to see what they were doing. Except
okay.
I didn't actually calculate the sums. So I was just, did that part in my head.
Okay, cool.
But it's going from 0 to 3 to 2 to 5 to 4. So it's kind of going up and down a little bit.
Yeah. If you do that, you can see what's happening, but you can also just notice that if you take that limit and then goes to infinity, the -1 to the n term is going to diverge. So that one's fine too. That way is fine too.
On part B, I started writing out some terms, but that wasn't overly useful because it's hard to see what's happening with that. So I decided just to go with the limit.
Yeah, on that one you can do the L'Hopital rule. Yeah, like you did. You can do the L'Hopital rule. Just determine that the bottom term is growing faster than the top one. Yeah, that part C is just kind of like, yeah, like you did. You just do 2 sequences sort of mashed together and they both converge. So therefore, yeah, the whole thing converges. Yeah, good. And then nth term for number 3. Everybody kind of see that one. You guys see what the formula is for that one? It's not quite as easy as that last one, but all right. So let me just quickly do that number 3. Everybody see what the terms of that sequence need to be. If you got -2/3 and 3/5, etc. So the fact that there's a minus sign there, that's telling you you're going to have a -1 to the n, and then the other stuff we have to figure that out. Anybody get a formula for this one? Like what's on the what should be on the numerator? The fact that we have that minus, again, every other term is negative, means we're going to have that. The first term is negative, so that corresponds. If you want so notice that in this case, all the odd terms are negative, right? All the odd terms are negative. And so that can be produced by this -1 to the n. If all the even terms are negative, you could change it to be that.
I was going to say, I see what I did there. That formula that I have written there is the general nth term. And then I guess it looks like I was focused on finding the limit of it is what I was doing.
Oh, I see. Oh, yeah, I do see it there. Okay, cool. Yeah, does it actually ask us? Oh, yeah, decide whether it converges or not. Okay, yeah, so the next term, since it starts at 2 and then it counts up by 1 every one after that, all you got to do is just say n plus 1, right? Since it's counting up by 1 every time. In the denominator, just notice that one you have to kind of see, well, it looks like it's kind of increasing exponentially, but not really because of the weird numbers. But if you look at the numbers that are 1 lower than all of those, then it makes sense, right? 2, 4, 8, 16, 32, that's hopefully obviously 2 to the n. And so the way that we produce that in the formula is like that, 2 to the n and then plus 1. And then the limit that Michael found works fine for that. It is definitely 0, it converges. And then the last one is determining whether it is monotonic, and so Michael went with the derivative route on that one and determined that derivative, you see -3/2 plus n squared, that is always negative. And so since it's always negative, the derivative is always negative, that means that the function is always decreasing, okay? And so therefore the sequence is always decreasing.